In this video, I want to talk about buffer solutions and titrations and how they relate with this Henderson-Hasselbalch equation. But let's say we have this aqueous solution. Let's say we have this aqueous solution, and let's say we have 2 molarity of this weak acid, this acetic acid. So let's just say we have 1 molarity here and 1 molarity here, but really we just have the solution of 2 molarity acetic acid. So we know if we have this 2 molarity concentration of acetic acid, this solution is going to be somewhat acidic because we have these acetic acid molecules reacting with water, and then they essentially protonate the water. And if you've taken organic chemistry, you know it's these electrons stealing the hydrogen. But the point is these waters get protonated by the acetic acid, forming hydronium. And then what's left is the conjugate base. So, but again, if we have this solution with these acetic acids, we know they protonate this water, and then this water gets protonated. And now the water is protonated and forms hydronium. And what's left is the conjugate base. But again, we've essentially increased this hydronium concentration. So we've increased this hydronium concentration, and again, we know the hydronium concentration dictates the pH. So therefore, we've essentially changed the pH. We have a lower pH, so we have an acidic solution because we have some of these weak acids. And again, we know this reaction has a very low Ka, so really it ionizes very little. So really just a little bit of these hydroniums or a little bit of these waters are protonated into hydroniums. But some hydronium is created, so therefore this would affect the pH. So therefore, in these original conditions with this solution, where we have 2 molarity of acetic acid, we would have an acidic solution. We would create some hydronium. These acetic acid molecules would protonate water molecules, forming hydronium, and therefore affecting the pH of the solution. So therefore, in this initial situation, we could represent this initial situation on this graph as this initial spot. So this initial spot represents this initial conditions, and then again, we could see the pH is lower than 7. We would have a fairly low pH, and therefore we would have an acidic solution. So this represents the beginning. But now, what if we add some of these hydroxide ions? What if we add some of this strong base to this solution? And again, as we add more hydroxide, we would add more equivalent, so therefore we would go in this direction in the graph, and we could see the pH would increase. And that makes sense. As we add more hydroxide, the pH would increase, and therefore it would become less acidic. Because again, when the pH increases, it becomes more basic. So therefore, as we add this hydroxide, this solution should become more basic. And we see as we add hydroxide, when we've had 1 equivalent of hydroxide, we see the pH has raised and has become more basic. So as we add these hydroxide ions, this solution will get more basic. So therefore, and then this represents once we've added 1 equivalent of hydroxide ions. And what that means is if we initially have 2 molarity of these acids, then once we've had 2 molarity of hydroxide, we've added 1 equivalent. We've added the same equivalent. So therefore, once we've had 1 equivalent, we would raise the pH to this amount, which we could see is above 7, and we'll explain why that makes sense later. But again, it's becoming more basic. So that's what and this is essentially a titration. We're titrating this solution with this hydroxide. But there are a couple points on this graph that's really important. So what happens? So we have 2 molarity. We have 1 molarity of each, so in total we have 2 molarity. But what if we had 1 molarity of hydroxide? So again, we have 2 molarity of this acid and 1 molarity of hydroxide. We can simplify this by saying, let's say we have 2 molecules of this weak acid, and let's say we have 1 molecule of hydroxide. But really, these are really in moles, so really you would have to multiply these by Avogadro's number. But I'm just simplifying it. Let's just say we have 2 molecules of this acid and 1 molecule of this base. Then when they react, what's going to happen? When they react, one of these is going to get deprotonated. This strong base is going to steal one of these hydrogens. So one of these are going to get deprotonated, so one of them is going to get deprotonated. And then so this reacts with this, where this gets deprotonated and this gets protonated, forming water. And again, nothing happens to this guy. This guy remains normal. So now we have 1 of these guys and 1 of these guys. So again, these reacted, where these 2 reacted, forming these 2 products. And then nothing happened to this guy. This guy's just like normal. So this is what happens when we add a half equivalent. Because again, we had 2 molarity and we've added 1 molarity. We had 2 molecules, we've added 1 molecule, so that's half an equivalent. If we added 2 hydroxide for these 2 molecules, that'd be 1 equivalent, but we've added half equivalents. So when you add half equivalents of a base, and again, we're focusing on an acid titrating with a base, then we have one equivalent of this base and 1 equivalent of this acid. So now we would have this solution, and again, remember, these were really in molarities, so we would have 1 molarity of this base and 1 molarity of this acid. So what would that look like here? Well, this is when we had 1 equivalent, so that's if we added 2 OHs, again, because we had 2 of these, so this would be equal to 1 equivalent, but we've added half an equivalent. We have 2 of these, and we added 1 of those, so we've added half equivalents of OHs. So therefore, we would be here on the graph. So that would represent this point of the graph, and this would be the pH. But this point of the graph, when we've added half equivalents, is really important, and that's just something you need to memorize on these graphs. It's when it's flat, and this is when we've added half equivalents. If we had added 1 equivalent, we would be here, but we've added half an equivalent, so we're here. And again, the solution would look like this, where we have 1 of these guys, one of these guys, and 1 of these guys, because again, we've added half equivalents, so only half of them turn into the conjugate base. However, what would be the pH of this solution? What would, again, so let's say we had 1 molarity of these, so they reacted with these, so now our solution has these guys. What would be the pH if we have these guys as our solutions? Well, again, we would just use the Henderson-Hasselbalch equation. So we would use the Henderson-Hasselbalch equation, so pH equals the pKa plus the log, the concentration of the base, so the concentration of the base, which is 1 molarity, and then divided by the concentration of the acid, which is 1 molarity. But something important, whenever we have log of 1 over 1, this gives us 0. You can plug in the calculator log of 1 over 1, or really log of 1, and this will give you 0. So this will turn to 0. So what we're left is with pH equals pKa. And this is not trivial. This is something you need to memorize. Whenever you have equal amounts of conjugate base and acid, whenever you have equal amounts, this goes to 0, and then the pH will equal the pKa of the solution. So this acid, and again, remember when using this equation, this is the pKa of the acid. This acid has a pKa of around, just simplifying it, let's just say 5.2. Let's say 5.2. Or let's just say 5. Let's just say that this has a pKa, this acid has a pKa of 5, and then we know this went to 0, so this pKa is 5, so we know the pH is 5. So we know the pH would be 5 in this situation. So this would be at 5, and again, I didn't draw this perfectly, but this would be at a pH of 5 at the half equivalence point when we have equal amounts of conjugate base and acid. Again, whenever we have equal amounts of conjugate base and conjugate acid, this cancels, and now the pH just equals the pKa. So now we know the pH of the solution will just equal the pKa of this acid. And not just that, when we have equal amounts of these, when we're at the half equivalence points, that's when we have a buffer solution, because we explained we have a buffer solution when we have a weak acid and its conjugate base, and if we have concentrations of both of those. And we see this makes sense. This does look like a buffer solution, because as we add more OHs, the pH doesn't change drastically. We see the curve is really flat. The slope, we have a small slope, so therefore the pH changes very slowly because the pH is being buffered because we have this buffer solution. So that's what's going on in this graph and these titrations. But again, when we had a half equivalence, when we had 2 of these and 1 of these, when we added half equivalence, only 1/2 of these were converted. So that's why we have 1 of these and 1 of these, because only half of them were converted to the base. So we have equal amounts. So then we have a buffer solution, and not only do we have a buffer solution, if you plug this into the Henderson-Hasselbalch, the pH will equal the pKa. So those are just things you need to memorize. The flat part is at the half equivalence point, and at the half equivalence point, the pKa of the acid the pKa of the acid equals the pH of the solution. So that's at half equivalence point. But what happens when we add an equivalent amount, when we're at 1 equivalent? So again, if we have 2 of these guys, let's say we had 1 equivalent, so therefore we would add 2 of these OHs. We would add 2 of these OHs. Because again, that's one equivalent. We have one equivalent of these, so we have 2 of these, and we have 2 of these. So one equivalent of these equals one equivalent of these. We have even amounts. So what happens in that situation? Well, in that situation, let's see, we would have 2 of these OHs reacting with 2 of these. And again, really these are all in molarities, but I'm simplifying it by saying we have just these 4 molecules. But again, this OH would steal this hydrogen, and this OH would steal this hydrogen. And we'd be left with these 2 compounds. These 2 acetate, these 2 conjugate bases. So now we would be left with these 2 conjugate bases. So now we have this conjugate base to react with water. Because again, we're in this aqueous solution, so now we have these waters, and now we have these conjugate bases stealing these hydrogens from waters, creating hydroxides, and therefore raising the pH and maybe making a basic solution. So one equivalent would be here. This is one equivalent when we added equal amounts of OHs to equal amounts of acid. So now we're at one equivalent, and we would see the pH would be around here. And the pH would be above 7, which makes sense, because again, we were left with these weak bases stealing these hydrogens, forming hydroxides, therefore lowering the hydronium concentration, increasing the hydroxide concentration, creating a basic solution, and that's why we're above 7. And notice here the pH is increasing rapidly. Why, when we have this buffer solution, the pH raises slowly, but once we get here, the pH raises rapidly? Because again, we've added those OHs, getting rid of these acids which were acting as a buffer essentially. When we were adding these hydroxides, they were stealing these hydrogens, but once all of these get used up, they start stealing hydrogens from water. Now those hydroxides will start stealing hydrogens from water, and once they start stealing hydrogens from water, we start drastically increasing the pH. And again, remember, these are in molarity, so it's not going to be exactly each mole of these is going to react with 1 moles of those, and 1 moles of those are going to react with 1 moles of those. We'll have 2 moles of these and 2 moles of these. So most of those are going to be used up, but most of the hydroxide that we add is going to use these up, and therefore as these were getting used up, we weren't changing the pH because we were just stealing the hydrogens from here. But once all of these get used up by these hydroxides, then the hydroxides start stealing the hydrogens from water, and then the pH starts to change. Once they start stealing the hydrogens from water, then hydroxides start to form, and as hydroxides start to form, the pH starts to change rapidly. So the key points of this video is one thing, when at the half equivalence point. So remember, at the half equivalence point is really important to just be familiar with what that looks like on this graph. So the half equivalence point is this flat part. And again, we said if we have 2 molarities of these and we had a half equivalent, so we had a half equivalent, so we had 1, then one of these get deprotonated and one of these don't, because we've only had half of equivalent. So at the half equivalent point, this is one equivalent. So at the half equivalence point, we have even amounts of conjugate base and acid. And when we have even amounts of conjugate base and acid, the pH of the solution equals the pK, because this gets canceled. So that's one key thing. When we're at half equivalence point, the pH of the solution equals the pKa of the acid. So that's one thing. And also that's when it's flat. But then, and again, this is when the solution is buffered. But then once we've added 1 full equivalent, that's when the solution starts to change drastically, and that's when the pH starts to change drastically.